All right, in this lesson, we're going to begin the study of plane and solid geometry. I've got the title up here, Plane and Solid Geometry, and this is a part of high school mathematics. When we look at high school mathematics, we see that we need 120 hours, and I know I repeat this at the beginning of every one of these high school classes, but it's important for you to understand what you need to do to complete the requirements for a high school diploma. 120 hours of math studies under the supervision of an instructor times 4 years makes for a total of 480 hours of high school mathematics. In high school mathematics, consist of basically 5 different mathematical sciences, but not really. The first is Algebra 1. The second is Geometry. The third is Algebra 2. The fourth is called Trigonometry. Or pre-calculus, or just pre-calc for short. And then the fifth is calculus. And as I explained at the beginning of all these math classes, the SAT test only tests algebra and geometry. So the end of Algebra 2 is the end of SAT prep math. Students who want to go to college should take 4 years of high school math. If they want to go to a selective college, they should take 4 years of high school math, and 4 years of high school math usually goes on to trigonometry. And students who are really serious about mathematics, who want to go into careers that actually work with mathematics, like engineering and mathematical careers themselves, they'll get into calculus. The minimum requirements would be 3 years of high school studies completing Algebra 2. A good college prep high school transcript will include a 4th year of math, and then if you get beyond that, you're just in rare company. Okay? In this course, we're going to be looking at this second study, geometry. And you can see the title is Plane and Solid Geometry. This is modern geometry. So we're not worried about classical geometry in this course. We're not worried about Euclid in this course. We just want to know what is required from the study of geometry for high school mathematics. That's what this course is for. All right? When we say plane and solid geometry, we're going to get into this in the book, but just so you know what these terms mean, plane and solid geometry. Geometry has to do with the study of magnitudes. We said that arithmetic is a study of multitudes. Geometry is the study of magnitudes. Magnitudes are wholes, right? We said a multitude is a collection of parts. A magnitude is a single whole. We study the number of multitudes. We study the size of magnitudes. Geometry is the study of magnitudes. It's about bodies and figures and shapes. That's what we study in geometry. Not multitudes, not numbers. There's no numbers in geometry. Okay? It's not about number. It's not about multitude. When we talk about plane and solid geometry, a plane, when we say plane, we mean a flat surface. A flat surface. A surface that has no height. So if I were to draw a flat surface, imagine this is like a sheet of paper, but not really like a sheet of paper, because even though a sheet of paper is pretty flat, a sheet of paper still has some thickness, right? It still has some height, even though it's almost flat. We can use it as an example, but it's really not a plane. A piece of paper is actually a solid. It's got length, it's got width, and it's got height, even though that height is very little. A plane would be a flat surface that has only width and length. It has no height or no depth. That's a plane, a flat surface. So you really have to imagine a plane, because you don't know what a plane, there's no planes in your life. You don't see a plane because it would be invisible, because it has no height. It would just be a flat surface. A sheet of paper is not a plane. It's like a plane, but it's not a plane. Okay? The surface of this desk is like a plane, but it's not a plane. A plane has no height. So that's what, when we say plane geometry, we mean the study of magnitudes that have only two dimensions. There are only two dimensions, length and width. That's what it means to be two-dimension. When we say something is 3D, you know the phrase 3D, it means 3 dimensions. 2D means just 2 dimensions, length and width. That's a plane. So geometry, plane geometry means the study of planes. And a solid, I'll draw a cube, a fancy cube here. If you imagine a cube has 3 dimensions. It has width, it has length, and it has height. 3 dimensions. Okay? Any figure that has 3 dimensions is a solid. Okay, called a solid. So a solid is a 3-dimensional figure. A plane is a 2-dimensional figure. So when we say plane and solid geometry, we mean that we're going to study the geometry of 2-dimensional and 3-dimensional figures. Understand that? Plane and solid geometry. So that title, plane and solid geometry, shouldn't be a mystery anymore. This study of plane and solid geometry, like I said, belongs to 10th grade. Belongs to 10th grade. So this is basically 10th grade math, plane and solid geometry. You're going to, if you've studied classical geometry, if you've studied Euclid, you're going to see a lot in this course that is in Euclid. But you're also going to see a lot of stuff that's not in Euclid. Okay, and we'll talk about why when we get to it. So that's all that I'm going to say about this course in introduction. We're just going to get into the study. Okay? You have a good idea of what geometry is, why we're studying it. It's part of high school math, what plane and solid geometry means. Okay? So let's just go ahead and get into the study and not waste any time. We don't want to waste time with high school studies because the main reason we're doing them is just to get a high school diploma, just complete high school studies. We have other studies that are more important. We want to have time to study languages and philosophy and theology. We can't just spend our time on modern high school math and let it take up all of our time. We want to get it done. We want to learn these subjects. We want to get through all these subjects. But we don't want to waste time going into them when really they're not worth studying too much. You're going to see they're simple studies as long as you work one article at a time. So let's go ahead and look at our book. The Elements of Geometry, a relatively modern textbook. I wouldn't say it's not a brand new textbook, obviously. It's an older textbook. I like to use these older textbooks because modern textbooks assume that kids are dumb and they fill the books with all kinds of goofy pictures and activities, and I just think all that stuff is a distraction. If you need that stuff, you're not a good student to begin with. These textbooks, they just get right to it. They tell you the definitions, they tell you the rules, they give you the exercise. There's no nonsense. You just get your work done and finish your studies. All right? That's why I like to use these older books. So to get started, we're just going to jump right into this. Elements of Geometry, Chapter 1. In Chapter 1, we talk about some preliminary topics. Preliminary means like preparatory. Preliminary means before you get started. So these are some preliminary issues that we have to discuss before we get started with geometry. Article 1 says, before the student begins the study of geometry, he should know certain principles and definitions which are of frequent use, though they are not peculiar to this science. They are very briefly presented in this chapter. In other words, there are some things that you need to know so that you can even talk about and understand the textbook in geometry. Some basic ideas. And we're going to take some time to learn those ideas before we get started with the study of geometry, okay? That's what preliminary things are. Principles and definitions which are going to be frequently used, which you need to take some time to become familiar with. And you can see, beginning in Article 2, because in geometry, we're going to prove a lot of things. We're going to do proofs. We're going to need to learn the vocabulary that we need in order to study and explain proofs. We're going to need to learn some logical terms. Logical terms. So Article 2 has a list of logical terms that we're going to need to learn to use for the study of geometry. So let's look at these logical terms. Some of them you might be familiar with from other courses. Some of them might be new. Article 2, every statement of a principle is called a proposition. And you see the word in capital letters is the vocabulary word. It's the logical term. So the first logical term is proposition. Every statement of a principle, is called a proposition. I'll keep a list of these terms up here just to keep it simple. So the first logical term, we're going to study logical terms. Don't write these definitions in your notes, just make a list of the terms you need to learn. The first one is proposition. You need to know what a proposition is. A proposition is a statement of a principle. Every statement of a principle is called a proposition. Every proposition contains the subject of which the assertion is made and the property or circumstance that is asserted about the subject. In grammar, you learned about subject and predicate. Give me a head nod. Subject and predicate, right? The subject is what you speak about. The predicate is what you assert about the subject. Every proposition must contain a subject and a predicate. The subject and the property or circumstance that is asserted of the subject. Every statement of a principle is called a proposition. When the subject has some condition, a condition means if. If this, then this. That's conditional. So we're not saying it's true. Like if I said, tomorrow, if it's sunny, we'll cut the grass. That's conditional. I'm not saying we're going to cut the grass tomorrow because it might rain. But if it's sunny, we will cut the grass. That's a conditional statement. When the subject has some condition attached to it, then the proposition is said to be conditional. Okay? Next, the subject with its condition, if it has any, is the hypothesis of the proposition. So you need to know what the term hypothesis means. Hypothesis. Hypothesis, that's how you pronounce that word. The subject with its condition is the hypothesis of the proposition. So a hypothesis is a part of a proposition. It's the subject with its condition, if it has a condition. The thing asserted of the subject is called the conclusion. So the conclusion is also part of a proposition. A proposition is made up of a hypothesis and a conclusion. The next logical term we have to learn is converse. Converse. And you're going to have time to study this because we're only going to have one class in plain and solid geometry a week. So you're going to have time to study this and go through it. Each of two propositions is said to be the converse of the other. The converse of the other when the two propositions are such that the hypothesis of one is the conclusion of the other. So two propositions are said to be converse when the subject, or the hypothesis of one is the conclusion of the other, and that's true for both of them. So the fourth term that you need to learn is converse. Moving on to Article 3 on the next page. We're just going to go through the logical terms here in this first lesson. A proposition is either theoretical or practical. A proposition is either theoretical or practical. A proposition is either theoretical or practical. Two kinds of propositions. There are two kinds of propositions, theoretical and practical. Remember, we're learning these logical terms because as we study geometry, they're going to be used all the time. When you go through the study of geometry, as you get going, you're going to run into these words, and you need to remember that these words were explained and defined at the beginning of the book. So you can just flip back to the beginning of the book and remember, oh yeah, hypothesis. I don't remember what that means, but I remember that it was explained at the beginning of the book, right? So you just have to remember to go back to the beginning and look it up. A proposition is either theoretical, that is, it declares that a certain property belongs to a certain thing, or it is practical. That is, it declares that something can be done. Propositions are either demonstrable, so this is another division of propositions. Propositions are either demonstrable, that is, they may be established by the aid of reason, that is, they may be proven. Demonstrable means to be provable, or they are indemonstrable. So we have two divisions of propositions. And we'll look back up on the board because I wrote this out. So proposition can be divided into different kinds in two different ways. Propositions can be theoretical or practical. theoretical when some truth is to be proven, practical when something is to be done. Propositions can also be divided between demonstrable, that is, they can be proven, or indemonstrable, they cannot be proven. So there are two different divisions of propositions. Two different divisions. And what this leads to is 4 different kinds of propositions. And I'll show you what I mean. Since there are 2 different divisions of propositions, there are 4 different qualities. We can have 4 different kinds of propositions. So on this side, I'm going to list theoretical and practical. And going this way, I'm going to list demonstrable and indemonstrable. You see that? Theoretical, practical, demonstrable, and indemonstrable. Now, if we put these together, we're going to have 4 different kinds of propositions, and they're listed there in your textbook. The first one is a theorem. Notice what it says. A theorem is a demonstrable theoretical proposition. A theorem is a demonstrable theoretical proposition. So the first kind of proposition is a theorem. A theorem is a proposition that is theoretical and demonstrable, able to be demonstrated, able to be proven, and theoretical. The second kind is a problem. A problem is demonstrable and practical. So demonstrable and practical is a problem. Okay, that's the second kind of proposition. The third kind of proposition is an axiom. An axiom is not demonstrable and is theoretical. So an axiom is the third kind of proposition. It's theoretical, like a theorem, but it's indemonstrable. It cannot be proven. Why can't it be proven? Why can't it be proven? The answer is because it's self-evident. It's obvious. There's no way to prove it because you don't need to prove it. That's what an axiom is. An example of an axiom would be a whole is greater than a part. A whole is greater than a part. That's an axiom. Do I need to prove to you that a whole is greater than a part of it? I don't need to prove that. It's indemonstrable. It can't be proven. Okay? That's an axiom. And then the fourth type of proposition is a postulate. A postulate is the fourth type of proposition. It's indemonstrable and it's practical. It's something that we do. It's something that we do. It's not demonstrable because it doesn't need to be proven. It's self-evident. It's obvious. So that Article 3 there teaches you that there are 4 kinds of propositions. These are the 4 kinds of propositions. And if you understand how propositions are divided in 2 different ways, when we combine these different qualities, we come up with 4 different kinds of propositions. A theorem, which is demonstrable and theoretical. A problem, which is demonstrable and practical. An axiom, which is indemonstrable and theoretical. And a postulate, which is indemonstrable and practical. Now that might be a lot to swallow at one time, but I think you'll understand it once you get a chance to go through it and study. All right? 4 types of propositions. And remember, these are the logical terms that we need to study and be familiar with in order to study geometry. Because you're going to see these words. You're going to see these words in your textbook. And so we're taking some time to explain what those words mean. And you need to remember, like I said, when you see these words, if you don't remember what they mean, go back to the beginning and review them. Okay? It'd be smart for you to memorize them. So if I were to say to you, how many kinds of propositions are there? How many kinds of propositions are there? 4. Okay? There's 4 kinds of propositions. Theorem, problem, axiom, and postulate. 4 kinds of propositions. And if I were to ask you, what is a theorem? What is an axiom? This chart, if you know what these things mean, will help you. And I'm not saying you know what these things mean yet. You're going to study it still. But you should know that what D, I, T, and P mean. If you drew this in your notes, if you were smart, you would draw this in your notes. Okay? This little chart should help you to remember what these things mean. Good, good. Okay? 4 types of propositions. Let's go on now under where it says a postulate, down to the end of Article 3. It says a proposition. So here we're learning a 5th kind of proposition. So we have 1, 2, 3, 4. And now we're being told, wait a minute, there's one more kind of proposition. It says a proposition which flows from previous principles is called a corollary. Corollary. A corollary. Now what that means is, let's say you're working in geometry and something is proven. And once you prove that, all of a sudden you realize, wait a minute, if that's true, then that means that this is also true. That's a corollary. When you prove something or something is proven and you realize that what you just did also proved something else, that's a corollary. Do you understand that? Okay? So sometimes when you're studying and working in geometry, you'll find that not only did you prove that one thing, but you also uncovered something else. That's a corollary. So now we have actually 5 types of propositions. All right? Moving on to Article 4. Oops. Moving on to Article 4. Let me get back to my spot. I just hit the page up button. Article 4. Reasoning by which a proposition is proved is called the demonstration. Reasoning by which a proposition is proved is called a demonstration. So when you hear the word demonstration, all that it means is proof. Demonstration is a proof. If you prove something, you demonstrate it, right? If you say, I believe in evolution, and I say, prove it, it's the same thing as saying, demonstrate it. Demonstration just means proof. The explanation of how a thing is done constitutes the solution of a problem. So what is a solution? The explanation of how a thing is done. And this is something that students always get wrong about math. When most students think about math, they think the solution is getting the right answer. But that's not the solution. The solution is an explanation of how to get the right answer. You understand that? In our arithmetic books, the right answer is often given with the exercises. It often gives you the problem and then tells you the answer. Why would a book do that if the solution was just to find the answer? Because that's not the solution. The solution is the explanation for how you get that answer. okay, how you get the right answer. Not just being able to get the right answer, but being able to explain how. That's one reason why in modern times it's deceiving to do work on computers and calculators, because you think you understand things that really you can't explain. You really don't know how to solve the problem. You just know how to get the answer using a calculator. And the calculator does the work, and you really don't know how it gets the answer, right? Like if I said find 25% of 250 and you used a calculator to solve that, you don't necessarily know how to find the percentage of a number. The calculator does because it's programmed into it, but you don't necessarily know the solution to that problem. In order for you to really understand mathematics, you have to know how to solve problems, not just find answers. You understand the difference? Okay? Because sometimes you'll get the right answer by luck and you can't do it again. You can't do it 5 times in a row. You can't do it if the numbers change. You really don't understand the solution. So the solution of a problem is the explanation of how a thing is done. That's a solution to a problem. There are 2 different kinds of demonstrations we're taught here. A direct demonstration. A direct demonstration proceeds from the premises by a regular deduction. Now I know you have no idea what that means, because it's kind of funny. We're studying a section about logical terms, and he's using logical terms to explain logical terms, which doesn't make much sense. All right? So what does that mean? A direct demonstration. What does demonstration mean? Let's see if you're paying attention. It's proof. Very simple. Demonstration means proof. Okay? I'll flip to the board up here. A demonstration is a proof. Very simple. We're shown here in our textbook that there are 2 kinds of demonstration. The first one is a direct demonstration, and the second one is an indirect demonstration. Okay? A direct demonstration, a direct proof, proceeds from the premises by a regular deduction. What in the world is he talking about? Well, let's take a look. This is where the classics teacher can explain the modern math. And if you don't know classical reasoning, you're going to struggle to understand modern math. That's why, the idea that you're going to study modern math instead of classical studies doesn't really work. So what does it mean to say a direct demonstration proceeds from the premises by a regular deduction? Okay? I'll give you a very simple example. Let's say that we have a question, we'll use an arithmetic example. All right? We have the number 4 and the number 7. And I say, prove to me that 4 is less than 7. Or prove to me that 7 is greater than 4. How could you prove that 7 is greater than 4? Well, everybody thinks that they know, but you don't necessarily know how to prove it. Prove it. The first thing we're going to do is state an axiom, because we're going to reason from an axiom, because an axiom doesn't need to be proven, right? An axiom doesn't need to be proven. So we want to start our argument from an axiom, because everyone will see that that first proposition is true. Okay? So I'm going to start with an axiom. And I'm going to say a whole, same axiom I just mentioned, is greater than a part. And I'm going to say that 4, or I should say, I'll say that. 4 is a part of 7. 3. Therefore, 7 is greater than 4. Does that prove that 7 is, yeah, that's proof. Okay? I start with an axiom because everybody knows that that's true. And I assume that we all agree that this is true, that 4 is a part of 7. And if this is true, and this is true, then this must be true. Do you see that? That's a demonstration. Now these first two propositions, these are called premises. They're the propositions that I reason from to my conclusion. This is the conclusion. So the premises are the two statements that we make, that we reason from to make the conclusion. And the conclusion is what we're trying to prove. All right? This is an example of a demonstration. In fact, this is an example of a direct demonstration, which is the first kind of demonstration that's talked about here. Direct demonstration proceeds, now watch this, ready? Direct demonstration proceeds, the textbook says, from the premises by a regular deduction. A deduction means reasoning that reasons down to a conclusion. Okay? That's a direct demonstration. That's the first kind of demonstration. The textbook then says, an indirect demonstration, so this is the second kind of demonstration, an indirect demonstration attains its object by showing that any other hypothesis or supposition than the one advanced would involve a contradiction or lead to an impossible conclusion. So this is a direct demonstration, right? We prove what we wanted to prove by reasoning from premises to a conclusion. If we can't do that, sometimes we can't do this. We can't make a direct demonstration. That doesn't mean we can't prove. We can prove it by an indirect demonstration. And an indirect demonstration is basically proving that every other possible answer is false. So there's two ways to make a demonstration. I can prove that the one statement is true. Okay? That's a direct demonstration. Or I can prove that every other possible statement is false and impossible. You understand that? So the only one that's left is the one that I'd like to prove. You got that? So let's say one of you stole my wallet. And I think Jacob did it, but I can't prove that Jacob did it. But I can prove that Isaiah didn't do it. I can prove that each boy didn't do it. Someone stole the wallet, and I can prove that it's impossible that any of the other boys did it, and you're the only one left. You see, that's a proof. That's not necessarily a proof, because there may be some other explanation, like someone else did come in and steal it. But in most situations, if I can prove that all of the other options are impossible, and you're the only option left, that's a way to prove something. That's an indirect demonstration. You see that? Okay? You understand that? Okay. So there's two kinds of proof, two kinds of demonstration. Direct, where you prove the thing directly, or indirect, where you prove that every other option is impossible. Indirect demonstration. When we do that, when we prove that every other option is impossible, that's called a reduction to absurdity, because the argument just becomes ridiculous. So that Latin phrase there, reductio ad absurdum, means reducing it to absurdity, reducing the argument to nonsense, basically. Okay? A work on geometry consists of definitions, propositions, demonstrations, and solutions with introductory or explanatory remarks. These remarks have the name of scholia. So scholia just means comments. Scholia, this isn't that important. Scholia just means comments that are made that explain things. Scholia, all right? That's Article 4. Article 5 is going to be the end of this first lesson. We're already good 40 minutes in. And it's just a note. It's a remark. So let's just read this. These remarks are sometimes made to the teacher, but it's good for the student to read. The student should learn each proposition. This is going to explain to you how you should study the propositions that we're going to see in the book. So that's very important, right? How to study a proposition. The student should learn each proposition so that he can state the hypothesis and the conclusion and the condition, if there is one, for the proposition. He should learn at each demonstration. So when you see the proof, because you're going to be given the proofs, you're not going to have to come up with the proofs. You're going to be told what the principle is, and you're going to be shown the proof. You just have to study it. All right? You need to be able to state the hypothesis and conclusion of the proposition, and you also need to look at the demonstration when you study the proof, and you need to state whether it's direct or indirect. And it's easy to tell, right? If it goes right from premises to a conclusion, it's direct. If it proves that all the other options are impossible, then it's indirect. So that's not difficult. If it is indirect, then what is the false hypothesis and what is the absurd conclusion that follows from it? It is a good exercise to state the converse or the converse of a proposition. In this work, the propositions are first announced in general terms, and I'll show you what this all means when we actually get to the proofs. But let's just read through this. In this work, the propositions are first announced or stated in general terms. The general enunciation is followed by a particular statement of the principle as a fact referring to a diagram. Then follows the demonstration or solution. In the latter part of the work, these steps are frequently shortened. So in the beginning, we're going to go through these steps carefully so you can see them. But later on, as we get through them and you get comfortable, we're going to skip some of these steps just so it's quicker. The student is advised to conclude every demonstration with the general proposition which he has proved. The student meeting a reference, that means a reference to some other proposition or to an axiom or a definition or a postulate. When the student meets a reference, he should be certain that he can state and apply the principle that's referred to by that reference. So now, I don't think you understand all of this stuff. I don't think you understand all the stuff in this first lesson. You have a whole week to study it and work to memorize these definitions and terms. But what I said before is important. It doesn't necessarily matter that you memorize and understand everything at the beginning. Often it's impossible to understand things at the beginning. It's like if I explained to you, imagine if I had a class and I explained to you how to use tools, but we didn't have any of the tools in the classroom. I just talked to you about the tools, and you never saw the tools, you never handled the tools, you never tried to use the tools. I just taught you how to use the tools with words in class. You're not going to know how to use the tools by just talking about them. We're going to have to go and actually see them and handle them and use them, right? So when we get into the propositions, then this stuff is going to make more sense because you're going to actually see it. And when we go through it, what's important is that when we start the propositions, when we start studying the propositions, that you always go back and look up the terms and the definitions and always refresh your mind about what the things mean. Do you understand that? What a lazy student does, a lazy student goes forward, sees a word he doesn't understand, and then he just says, I don't understand this. This is confusing. I'm lost. Right? A good student doesn't necessarily know and understand everything, but he goes and looks it up. That's the difference. One student says, I don't know. That's just lazy. That's quitting. A good student will say, hold on a minute. Let me go back and look up the definition of that word. We learned it in the beginning. All right? So you have to commit to be that kind of a student. You can't just quit and play dumb and say, I don't know. That's just lazy. Of course you don't know. You're a student. But the answer's in the book. So the right response is, wait, let me go look that up. And it's okay if it takes time. That's the way a good student works. Right? When you feel that you're confused, when you feel that you're reading something and you don't understand it, usually it's because there's a word that you forgot, there's a definition you forgot, and you can choose at that point to just say you're confused and quit, or go back and look it up and then go and reread that passage. Okay? So we have a week to work on studying this stuff, but you're really not going to understand it until we start doing the work of studying propositions, and then it's going to make more sense. We'll go back and review it, so it'll make more sense and you'll understand all this stuff, okay? So that's everything for our first lesson in plane and solid geometry. What should you know at this point? You should know why we study geometry. You should know the difference between this geometry we're studying and classical geometry. It's not the same thing, okay? This is high school geometry. This is for a high school diploma. This is for a college application. If you want to become a master of geometry, you're going to have to study classical geometry and classical reasoning. This is modern school geometry. It's usually taught in 10th grade. So you're studying 10th grade math in this course. You should understand what geometry means. It's the study of what? What kind of quantity do we study in geometry? Magnitude, right? It's different from arithmetic. Arithmetic is the study of multitude. Geometry is the study of magnitude. When we say plane and solid geometry, who can tell me what a plane is? What is it? A flat surface. Good. How many dimensions does a plane surface have? 2 dimensions. What is a solid? How many dimensions? 3 dimensions. Another word for solid is a body. Okay, a body is 3-dimensional. So plane and solid geometry means we're studying magnitudes, and the kinds of magnitudes we're studying are planes and solids. All right? And then as we get into this first lesson, the textbook author said, look, before we get into geometry, you have to learn these logical terms, because we're going to use them all the time. And we have to do the work of studying these terms, learning these definitions, so that when we start studying the propositions, we understand the words we're going to read. Okay? And if you don't remember what the words mean, when you see them in your lesson, what do you need to do? Go back and look them up. You don't have to remember everything. Go back and look them up. Okay? So that's all for lesson 1.